Hi, I'm Ben-Yaakov. This presentation is entitled A Different Equation of Gapped Cores A sub L, or subtitled More Intriguing Magnetics Equation. So what is A sub L? A sub L is the inductance you'll get if you have one turn on a core, and it is usually for one turn, the value in inductance, Henry per turn. Sometimes it's for 1,000 terms. You have to look up to see what's the definition in a particular data sheet. So therefore, if you have a core and you have n turns, then the total inductance you'll have is n squared times A sub L. So in this presentation, I'm going to show that there is a very intriguing, a very interesting relationship relating the size of the core to A sub L. Let me start off, however, with the development of the gapped core permeability, or the equivalent permeability of a gapped core. So here we have a core, we have n turns, we have the magnetic path length within the ferrite, H sub F, we have the length of the gap, L sub G, we have the cross-section area of the ferrite, which is also the cross-section here. I'm assuming B is constant all over, save the fringing effect, which I'm neglecting. Okay. But then we have, of course, magnetic field within the ferrite. This is H sub F, and then we have a magnetic field within the gap. So B is constant. The total length is the sum of the length of the gap plus the length of the ferrite, and in most cases the L sub T is sort of approximated by the length, the magnetic path length within the ferrite, because L sub G is normally like a millimeter. Now, starting with HDL is equal to N times I, then we have the sums of HF times LF, this is here within the ferrite, then we have the magnetic field within the gap times the length of the gap. This will be the total H times the total length. Now replacing H by B over mu here and here and here, and then crossing out B, I'm getting this equation which relates again the different length and mu to the equivalent. Here, instead of H sub T, I've put B over mu 0 times mu sub E, which is the equivalent permeability of the total core. Now going on, I'm getting this relationship, and then I find that mu sub E is equal to this expression, and then if this term is much smaller than L sub G and LG is much smaller than L sub F, then I'm getting that the equivalent permeability of the total core is L sub F over L sub G. That is the distance or the magnetic path length within the ferrite times L sub G, which is the gap length. This is well known, and this holds when, again, this is smaller than this, again, this is smaller than this, or when the mu sub R, relative permeability of the ferrite, is larger than LF over LG. This normally is the case because mu sub R is the range of thousands, and then LF over LG, LF could be 100 millimeters, and this would be 1 or 2 millimeters. So this is normally much larger than this. So this relationship holds over quite a wide range of situations. So what we found now that we can express mu sub E, the equivalent, by LF over LG, and now I'm turning to the equation of the inductance of an inductor. If we have an inductor with a cross-section area of A sub E, magnetic path length LE, and then we have n turns, then the inductance will be this relationship. Now I'm replacing now mu sub E by this relationship, and therefore I'm getting this expression for the inductance, n squared times A sub E, cross-section area of the core, over the length of the gap, times mu sub 0. Mu sub 0 is here, this is the value approximately, this 0.5 here. So A sub L is this inductance for one turn, and lo and behold, we are getting that A sub L is equal to the cross-section area of the core times the length of the gap times mu 0, independent on any other relationship, any other parameters of the core. And this is sort of a universal expression. So I've decided to sort of see how good is it? I mean, how good does it really represent actual cores? So I've done some calculation here for different cores. One is the pot core, 4229. This is the cross-section area. There is another core, E65, with 535. It's a big core. And then a smaller core, which is RM, another shape, RM, with 200 millimeter square of a cross-section area. And from the data sheet, I got the value of A sub L for different gaps. This is the gaps in micrometers. So this is 1.3 millimeter. Goes from 1.3 millimeter to 0.19. So this is the value given by in the data sheet, and this is the calculated one. And you can see that it's pretty close. It's not exactly, because there's many approximation here. First of all, the fringing effect and some other factors. And in general, however, we see that it's a pretty good approximation. At least it gives you an impression of what is the AL. Here it's 315. This is in nanohenry per turn. And here I'm getting 241. 400, 321, and up to 1600 I'm getting 1670. So it's pretty close. And here again for this E65 go up to 4 millimeter gap. We see here 1200, see approximately the same number. This is 700, 642, 526, 400. And here it's a little bit off. This is 230, and this is 161, and this is for the very large gap of 4 millimeters. Again, there's this fringing effect. And you can see also in the RM14, the numbers are pretty good. This is 160, 126, 250, 240, 400, 480, and 1000. Again, this is for the small gap. We have 1600. So we can then say that this approximate equation is really not sufficiently accurate for design, but it really gives you a feeling of the expected AL of a given core. So all you need is just the cross-section area and the gap you're going to use, and you know immediately what is A sub L. Kind of very interesting, I think. So this brings me to the end of this short presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.